Okay, let's talk about energy. So energy is the ability to do work. There's two main types of energy we'll talk about, and that's kinetic energy and potential energy. Kinetic energy is the energy of motion. So any moving object has kinetic energy. Potential energy, though, is determined by the position of an object or by the chemical composition of a substance. So for example, a boulder on the top of a mountain has a lot of potential energy. When it starts to roll down the mountain, the potential energy changes into kinetic energy because the object is now moving. Okay, the units of energy are a joule or a calorie. A calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. 1 calorie equals exactly 4.184 joules. So let's do a little practice here. So a defibrillator gives a high energy shock output of 360 joules. What is this quantity of energy in calories? So we know 1 calorie is 4.184 joules. So we set up our problem. We start with 364 joules, and we multiply that by 1 calorie over 4.184 joules. Our units cancel, and we're left with 86 calories. Let's talk about energy and chemical and physical change. Chemical and physical changes are usually accompanied by energy changes. So, for example, in a physical change, water evaporating on our skin, water molecules absorb energy, which cools the skin. In a chemical change, burning natural gas on a stove, energy is released, which heats the food we're cooking. The release of energy during a chemical reaction is analogous to the release of energy when a weight falls to the ground. Systems with high potential energy have a tendency to change in a way that lowers their potential energy. Objects or systems with high potential energy tend to be unstable. So if you look at this picture here, we have a weight on top of a building. It has a lot of potential energy. It's really unstable. So as it falls to the ground, the potential energy lowers. It's converted to kinetic energy. And when it hits the ground, it has really low potential energy and it's very stable. And it might release that energy as heat. Let's talk about exothermic reactions. Some chemical substances have high potential energy, such as TNT. TNT molecules undergo rapid chemical changes that lower their potential energy, and this is why it's explosive. So reactions that release energy are called exothermic reactions. So that means our reactants start at a higher energy, our products are at a lower energy, so energy must be released as we go from reactants to products. And again, this is called exothermic. Endothermic reactions are the opposite. So some chemical reactions have to absorb energy from their surroundings as they occur, and again, that's called endothermic. So an example of that is a chemical cold pack. As you break open the pack, the chemicals inside react, and they absorb energy from their surroundings, which cools your skin. So again, if our reactants start at a low energy, and they absorb energy to become products, that's called an endothermic reaction. If a particular reaction is exothermic, then its reverse must be endothermic. So here's an example. Evaporation of water from skin is endothermic. It cools you off. But the condensation of water onto skin is exothermic, which is why steam burns cause pain. Let's talk a little bit about temperature. Usually we use degrees Celsius or Kelvin. Temperature is a measure of thermal energy. Atoms and molecules that compose matter are in constant motion. Heat is the transfer or exchange of thermal energy caused by a temperature difference, and heat has units of energy. To convert between Kelvin and Celsius, we use this equation right here. So the temperature in Kelvin is equal to our temperature in Celsius plus 273. Okay, let's talk about specific heat. The specific heat capacity, or C, for a substance is defined as the amount of heat needed to raise the temperature of exactly 1 gram of that substance by exactly 1 degree Celsius. We have two units. We can either do units of calorie per gram degree Celsius or joules per gram degree Celsius. A high specific heat means that substance can absorb a lot of energy with minimal change. So let's talk about water a little bit. Water has a high specific heat. Its specific heat is 1 calorie per gram degree Celsius, or 4.184 joules per gram degree Celsius. That's a high specific heat. That means you have to put a lot of energy into water for its temperature to raise. So an example of this is coastal cities. So coastal cities, you have that big body of water, and that big body of water absorbs heat in the summer, which keeps the land cool. And in the winter, it releases heat, which keeps the land cool. And that's why coastal cities tend to have pretty moderate climates and don't change much throughout the year. An example of that, if you've been to San Francisco, it's pretty much always 70 degrees there, year-round. That's because of the huge body of water, the San Francisco Bay, that surrounds the city. Inland, though, you don't have that heat-regulating body. The earth and rocks, they don't have a high specific heat. So that's why inland, you tend to have huge temperature fluctuations throughout the year and even throughout the day. Right now in Colorado, it's 90 in the 80s or 90s during the day, and we're getting down to the 50s and 60s at night. And that is a big part of why. Okay, so we also will do calculations with specific heat. So when a substance absorbs heat, which we denote as Q, its temperature change, delta T, is directly proportional to the amount of heat absorbed. So then we have this reaction, or with this equation, right, where we say heat is equal to the mass of our substance times its specific heat capacity times temperature change, or Q equals M times C times delta T. Q, again, is the amount of heat in joules, M is the mass in grams, C is the specific heat capacity, and delta T is the change in temperature. Q could also be in calories. We just need to watch our units of C, right? I said before, C can be in joules per gram degree Celsius or calories per gram degree Celsius. So depending on which C you use will change what units Q is in. So that's just something to watch out for. So let's do an example. Gallium is a solid metal at room temperature, but it melts at 29.9 degrees Celsius. If you hold gallium in your hand, it melts from your body heat. So how much heat must 2.5 grams of gallium absorb from your hand to raise the temperature of gallium from 25.0 degrees Celsius to 29.9 degrees Celsius? The specific heat capacity of gallium is 0.372 joules per gram degree Celsius. So we use this equation, Q equals MC delta T. The first thing we want to do is calculate delta T, which is T final minus T initial. So our delta T here is 29.9 degrees Celsius minus 25.0 degrees Celsius. So that equals 4.9 degrees Celsius. So now we just fill in the equation. We have Q equals M, which is 2.5 grams. We have our specific heat, which is 0.372 joules per gram degree Celsius. And we multiply that by our temperature change, which we calculated to be 4.9 degrees Celsius. And we get a Q of 4.6 joules. Again, we have our answer in joules because we use a specific heat in joules per gram degree Celsius.